Hello dear students, I hope you are doing well. Today we are going to talk about the carbon-13 NMR spectroscopy. We are done with proton NMR spectroscopy. We will discuss a few features about the carbon-13 NMR spectrum and we will learn how to read it. Just to remind you that the basic concepts that we have studied for proton NMR is equally applicable to carbon-13 NMR. So we will not discuss the basic principle that is exactly the same, but we will spend more time on reading the spectrum. So let's start. So as I told you earlier that there is a slight difference between proton and carbon-13 when it comes to NMR, and one of the basic difference is their Larmor frequencies under the same conditions of applied magnetic field. So you see that when we have similar magnetic field strengths like 7.05 for both proton and carbon-13, the Larmor frequencies are different. That is, the carbon-13 frequency is 4 times less than that of proton. Similarly, the galomagnetic ratios of both of them are also different, and that is by a factor of 4. The natural abundance of carbon-13 is only 1%, that of proton is 99%, which means that proton is more sensitive as compared to carbon-13, and to have a good carbon-13 NMR spectrum, you would require larger quantities of your sample, so as to increase the percentage of carbon-13 in your sample. Now, we can have two types of carbon-13 NMR spectra. The first one you can see here is a proton-coupled carbon-13 NMR spectrum, and here we have the decoupled carbon-13 NMR spectrum. A proton-coupled spectrum is the one in which the carbon nuclei are coupled with the protons attached to that particular carbon atom. For example, if a carbon has one hydrogen attached to it, just like the coupling we discussed for proton, this proton can be seen by the carbon in both alpha and beta states, and that is why the signal of the carbon atom to which that proton is attached will be split into two, according to N+1 rule. If a carbon has two protons attached to it, then the signal will be split into 3, according to N+1 rule, and if a carbon is attached to three hydrogens, then the signal will be split into 4 according to N+1 rule. In a proton-coupled spectrum, you would see this multiplet. So you can see here that we have a singlet, which means that this carbon does not have any hydrogens attached to it, which means it's a quaternary carbon. This signal appears as a doublet, so that means that only one hydrogen is attached to the carbon. It's a CH. This one is a CH. This is a CH. This is a singlet, so it's a quaternary carbon. We have triplet here, and that means it's a CH2. And you can see here that we have 3 quartets. If you look at it closely, these are 3 quartets, but somewhat merged with each other. So these are 3 CH3 groups. The problem with the proton-coupled carbon-13 NMR spectrum is that the intensity is sometimes lower. So to increase the intensity of the signals, what we do is that we decouple the protons. And you can see now the same molecule, the same carbon-13 spectrum, but now it is a decoupled carbon-13 spectrum, and you can see the intensity increases for all the signals. But the problem with the decoupled carbon-13 NMR spectrum is that we do not have multiplets. We have only singlets. So as we can identify the CH, the CH2s or the CH3s in the proton-coupled spectrum, we cannot differentiate between these carbon atoms in the decoupled carbon-13 NMR spectrum. However, the spectrum is more clear because there is no congestion. You can see the overlapping. These singlets do not overlap with each other. So it's a clear spectrum with good intensity, and the problem of differentiating between these carbon atoms can be solved through a different technique. So you can see here this is a singlet, which was a singlet in the coupled spectrum as well. It's for the quaternary carbon. This CH also appears as a singlet. This appears as a singlet. This one CH appears as a singlet. This this CH2 appears as a singlet. So all are singlets. But how to differentiate between these carbon atoms, like the quaternary carbons, the CH, the CH2s, and the CH3s, we can do this by the attached proton test. So we perform a test in which we determine how many protons would be attached to a particular carbon atom. So there are different techniques. One of them is INAPT, insensitive nuclei enhancement by polarization transfer, that can tell you or differentiate you help you differentiate between these different carbon atoms, but that is not normally used nowadays. The technique that has replaced INAPT is distortionless enhancement by polarization transfer, that is the depth experiment. And this depth experiment helps you determine the multiplicity of the carbon atoms. Now, as I have told you earlier, that in different NMR experiments, the only difference is the pulse sequence, and that is the soul of all NMR experiments. The pulse sequences may be different, the phase angles may be different, the duration may be different. So each of these different types of techniques have a different pulse sequence. Depth also has its own pulse sequence, maybe involving more than one pulses. The last pulse is known as a theta pulse. So the pulses before this theta pulse are of fixed angles, phase angles for all the experiments, but the last pulse can be changed, and that is why it is written as a theta pulse. So you can have different phase angles for the last pulse to differentiate between CH, CH2s and CH3s. So we can have 3 or 4 different types of depth experiments, which are known as the depth 90, the depth 135, and the depth 45. The depth 90 means that the last theta pulse is 90 degrees, 90 degree pulse. Depth 135 means that the last theta pulse is of 135 degrees, and depth 45 means that the last pulse is of 45 degrees. So let's see the effect of this theta pulse on these different carbon atoms. So we have the angle here, the theta angle, and this diagram shows some waves. This wave, this dotted line is for CH, this type of dotted line is for CH2, and this solid line is for CH3. So if we give a 45 degree pulse, the last theta pulse is 45 degree. So the waves generated from these carbon atoms, the CH, the CH2s, and the CH3s, all are positive when we give a depth when we give a 45 degree pulse, and the technique is known as depth 45. So what we see in depth 45 is that the CH is positive, the CH2 is positive, the CH3 is also positive. Quaternary carbons do not appear here. So in all depth experiments, you will not see any quaternary carbon. All right. Then if we have a 90 degree theta pulse, so you can see that in a 90 degree theta pulse, the CH wave is positive. This CH3 wave falls to 0, so the amplitude is 0. This CH2 also falls to 0. So in a depth 90 experiment, you will only see signals for CH carbons. You won't see CH3, CH2, or quaternary carbons in depth 90. What about depth 135? So you can see that when we have a theta pulse equal to 135 degrees, then the peaks or the waves for the CH and the CH3s are in positive phase, and that of CH2 is in a negative phase. So what has these waves to do with the spectrum? The intensity or the amplitude of these waves will tell you, or the phase of this wave will tell you the position or the phase of the peaks for these different types of carbon atoms in the depth experiment. So for example, we have a depth 45 spectrum. You will see the CH, CH2s, and CH3s in positive phase. If we have a depth 90 experiment, we will only see CH signals in positive phase. If we have a depth 135 experiment, you will see only CH2s in the negative phase, and CH and CH3s will be in the positive phase. In none of these experiments will you find the quaternary carbons. Quaternary carbons will only be seen in the broadband spectrum. This is known as the broadband carbon-13 NMR spectrum, which contains all the carbon atoms from your molecule. So let's see an example of depth experiment. So we have the broadband spectrum of this molecule. We have the depth 45 spectrum here, the depth 90 is here, and the depth 135 is here. So you have the structure here. The carbon atoms are labeled as 1, 2, 3, 4, 5, 6. The chemical environment or magnetic environment of these two CH2s is the same, so they will have the same chemical shift value as we have discussed for proton signals. So they will have only one signal and the rest are different, so they will have different signals. So in all, you should expect to see 5 signals. So 1, 2, 3, 4, 5, and 6, sorry. So 6 signals. So you will see 6 signals for 6 different types of carbons. In all, it has 7 carbons, 1, 2, 3, 4, 5, 6, 7. But the signals are 6. This is for the carbon of the chloroform. Now, in broadband carbon-13 spectrum, you will see all the carbon atoms. Although we have labeled it so you can differentiate, but if it is not labeled, go to depth 45. So depth 45, if you remember, will give you positive signals for CH, CH2s, and CH3s. So you see 1, 2, 3, 4, 5 signals here. This signal is missing. So you don't see any quaternary carbon in depth. That you should keep at the back of your mind, which means that this signal belongs to a quaternary carbon. So you can identify the quaternary carbon in the structure. That is your carbon number 6. So which means that this signal belongs to carbon number 6. That is the quaternary carbon or the carbonyl carbon of the ester. The rest are CH, CH2s, and CH3. Now how to differentiate between the rest of the 3? So we have a depth 90 spectrum here, which only gives signals for the CH carbon atoms. You see only one signal here, and you can see that in your structure you only have one CH. So this signal belongs to this CH, the carbon number 2. If you go down here in depth 45, this signal belongs to CH, and if you go down into the broadband, this signal belongs to the CH. So now you have differentiated between quaternary carbons and CH carbons. What about the CH3s and the CH2s? Go to depth 135. So in depth 135, you will see negative signals for CH2s. So you see 2 signals here in negative phase. So these 2 signals would belong to the CH2s and the rest would belong to CH3s. So in the positive phase, we have CH and CH3s here in the depth 135, but you already know that this signal belongs to CH, so rest of the 2 belong to the CH3s. These 2 will give one signal and this one will give a different signal. So these are for 1 and 5, this is for 2, this is for the CH2, the third one, this one, this is for CH2, the fourth one, and this one is for the quaternary carbon. So this is how you can differentiate between these 4 different types of carbon atoms. Let's see another example. So we have acetyl salicylic acid. This is the broadband carbon-13 NMR spectrum of this aspirin. You can see 1, 2, 3, 4, 5, 6, 7, 8 different types of carbon atoms. So you should expect 8 signals, 1, 2, 3, 4, 5, 6, 7, 8. Now we have to differentiate between the CH3s, the CH2s, the CHs, and the quaternary carbons. I have labeled them here with different colors. So let's go down to the first depth experiment, that is the depth 90. Depth 90 will tell you about the CH only. So you have 4 signals here. That means you have 4 CH carbons, and they all appear around 120 to 135 region. That is the aromatic region, right? We will discuss the scale later on, but this is the aromatic region. So you can see in this structure as well, we have 1, 2, 3, 4 CH carbon atoms in this range. So let's go down to the broadband again. So these are the 4 CH signals. Now we need to know where are the CH3 groups and the CH2s, if any. There is no CH2 group or the quaternary carbons. So let's go down to depth 135. Depth 135 will show you positive signals for CH and CH3s and negative for CH2s. So you already know that these 4 signals belong to the CH of the aromatic ring. Now the only signal left behind is this, which means this should be a CH3. No signals in the negative phase, no CH2 groups, and you can see in the structure clearly. So this signal at 20.8 belongs to the CH3 group. So this one is for the CH3. Now we are left behind with quaternary carbons. So all of them, the rest, belong to the quaternary carbons. So you should expect 3 quaternary carbons, or in fact 4 of them, 1, 2, 3, and 4, right? So we have these 4 quaternary carbons. This is also a quaternary carbon that is hidden here, all right? So this is how you can differentiate between these different types of carbon atoms from the depth experiment. Now here's the chemical shift values of these different types of carbons. So again, the same range, so the same shielding and de-shielding effect. So when you go closer to 0, the shielding increases. When you go downfield, the de-shielding increases. This region is known as the upfield region. This is the downfield region, and this range goes from 0 to around 210. Let's see where you can find these different types of carbon atoms. We start off with TMS, that is again arbitrarily set at 0. Then you will find the sp3 hybridized carbons around 10 to 30 ppm, and that is the methyl carbons. The CH2 carbons would appear slightly downfield from 15 to around 50 depending upon their chemical environment, and CH and quaternary carbons will also appear in almost the same region, extending up to 60 ppm. Then we have the carbons attached to heteroatoms like halogens and oxygens, so they may extend up to 80 ppm. And if we have acetylenic, this is for nitrogen, there is a slight mistake, so you can take it as a nitrogen. But if you have acetylenic carbon atoms, they appear from 60 to 90 ppm. If we have olefinic carbons, the sp2 hybridized carbons, just like the protons of olefins, they will appear downfield again because of the same effect. So 10 to 100 to 150 ppm, you will find these olefinic carbon atoms. The aromatic carbons still appear slightly downfield because of the ring current effect. So they appear up to 170 ppm. Then we have the carbonyls of the acids, ester, amide, and anhydrides. And finally, we have the carbonyls of the aldehydes and ketones. They have a huge range, all of them. Depending upon their chemical environments, they may vary. So this is an introduction of the carbon-13 NMR spectrum, and we will jump on to the structure elucidation part after this, and we will see how we can use proton and carbon-13 NMR spectra for determination of the structures of the molecules. So thank you so much, and see you with the structure elucidation session. See you later.